Hello, hello. Okay, let's begin, everyone. Here is a lecture summary, daily lecture summary, and I'd like to remind you to put the date on the signature sheet. Okay, many teams forgot the date, and it could be hard for me to put in the right pile, just in case. And the next item is not the whole, but I just want to show you the first link, which came from my finite element course in fall 2008. So if you click at the link, I want to show you the animation of the vibration modes of an electric pylon. Okay? So that you see that what you learn in this course is applied to finite element method, and the electric pylon is not the simple spring and damper in series. Okay, so it looks as follows. So if you click at that link, it will bring you to this Wikiversity site. This is the team in the fall 2008. They call themselves Team Bike. I also divided by team, but at the time I did not have a computer code to divide into teams, to do team formation. So the students selected the names for their teams. So this is Team Bike, and if you scroll down to the bottom, so you see this is the electric pylon here. So very sophisticated, right? Structure. It's not just the 3 springs in series. And you want to do the eigenvalue problem, generalized eigenvalue problem of this electric pylon. And down here is the animation. So you see they have the code there, and this is the animation. It's pretty long, as you see towards the end. Okay. And yeah, so you see the animation. This is mode 1. See, mode 1 is, this is the fundamental mode, the mode with the lowest frequency. It's like you are doing exercise like this, okay? So it's clearly much more sophisticated than the 3 springs in series. And this is mode 2 with higher frequency, and this is like weightlifting mode, like an athlete lifting the boat, and this is like the ball and the 2 hands here, and notice the mode shape. Okay, and the third mode is also like I call this the dancing mode. So it's like it's dancing, right? Very nice, and it's still running after all these years. Okay, so the lesson learned is that the method that you learn in this course is applicable to really general systems, very sophisticated structures. And there are many more modes depending on the number of unknowns. Okay, so in this particular structure, there are many unknowns. Each node that you see here has 2 displacement degrees of freedom. Okay? All right, so that's all I wanted to show, to talk about this, so that you can connect what you learn to real world problem, and I'll mention the other examples later, because I'd like to coach you to do exam 1.2. Okay. The first, and let's begin with the critical thinking question. As customarily done, I have my handwritten notes with annotation from the previous lecture, always listed after the topics covered. And the first critical thinking question is when you solve a linear second order ODE with constant coefficients, and when the discriminant of the characteristic equation is 0, right? That's case 2. And you have one double real root. And this is not the first time you saw this in differential equations. You saw in the extra lectures in my course, and also in my lectures in class as well. Okay. One double real root question. What is the meaning of the word double in double real root? Why double when there is only one root? Anyone? Critical thinking question here for active learning credits? Yeah, I need to get my list. While I do that, why don't you think? You can discuss with your teammates also. Feel free to talk to your teammates. Why double real root? Okay, Mark is very fast. Mark of team A, hang on. Yes, Mark, go ahead.
Is it because each part of the homogeneous solution is a solution itself to the equation?
Each part of the homogeneous solution is the solution itself.
Yeah, so you find the first one and then you find the second one. Both the first one and the second one by themselves are solutions.
Both the first one and the second one. Okay, so here, let's recall that we are talking about the roots of the characteristic equation. So let me remind you. Okay, so let me bring up the previous meeting 24 here, and probably down below. Yeah, so I review to you here, right? So this is how you would decompose a linear second order ODE with non-zero excitation into a homogeneous problem and a particular problem. And when you solve a homogeneous problem, you get a characteristic equation, right? So, and this is, I give an example of a one double real root, okay? And so here you have one root, but I'm asking for the meaning of the word double. I saw Frank Bristol. Could you please remind me? I know team 7, right? Tony, yes.
Isn't it just called double real root because you get the same root twice, so like you get a double?
Very good, yes. You get the same root twice, and how do you see that? Well, here is how you see. Here is how you would see, so let me bring up my notes for today. And I also have the notes from the previous session. And what I do is I copy this example here, okay, to the new notes. Okay, and let me zoom in. I am explaining the meaning of the word double in the terminology. One double real root. So see sample below for meeting 24. Okay. And so this is coming from meeting 24. You see, instead of writing like this, and like Tony said, you could have written lambda minus 3 squared as lambda minus 3 times lambda minus 3 equal to 0. Okay, then you get the same, or you get the following. You can think of this like this. You know, in general, suppose that you have, instead of writing like this, okay, I write like this. I write lambda but with the subscript 1 and 2, right? So what would be, and lambda 1 and lambda 2 are just two numbers, right? So how do you solve this equation? It's very simple. Each factor has to be equal to 0, so you have two roots, lambda equal to lambda 1 and lambda equal to lambda 2, okay? So what I was saying is that here, you deduce that lambda equal to lambda 1 is the first root, and lambda equal to lambda 2 as the second root. Okay? So essentially that. Okay. Example. Let's take a concrete example so everyone is on the same page. Because I know some students work better with numbers, so let's plug lambda 1 equal to say 1. Anyone wants to suggest lambda 2? Anything, any number that you can think of. Come on, get active learning credit. Let me note down Tony. Come on, suggest a number. Any number.
3.
Tony. 3? Okay.
Hi.
26. Who suggested 3? What's your name? Sorry?
Team 3.
Team 3. What's the name?
Blake.
Blake. Okay.
Right answer, right?
Yeah, you know, I mean, any number, this is just an example, okay? And so if you plug 3 here, then the result is that you have two roots, right? 1 and 3, that's all. Of course, if you multiply out, you get a quadratic equation, okay? So this would be 1 and 3. So that's just an example. So, so what it says here is that you have two roots, and if we call lambda 1 is the first root, and lambda 2 the second root, then they have the same numerical value. So that's why it's a 1 and double, because you know the same number it's like a root twice. That's why it's called double, but there's only one numerical value. Okay, so that's the meaning of the word double. Any questions on this? Okay. The next critical thinking question is related to the exam, and so I might as well go directly to that and give you. So let me pose the question here. You recall when I explained how to find the model initial condition. Instead of inverting the matrix phi bar, you can use orthogonality to avoid doing the inverse. Okay, so the question is, can you express the inverse of the matrix phi bar? I will replace this with the actual equation image or a variable image. Okay, so I just added this just now. So phi bar is the matrix of the normalized eigenvectors, okay, by the matrix phi bar and the mass matrix. That's one of the questions in exam 1.2. So let me see whether I have, yeah. So this is exam 1.2, and let me show you where that question would be. That's in problem 4, and the question is right here. 5A. From the orthogonality of the normalized eigenvectors with respect to the mass matrix, find the expressions S, but if you find one, that's pretty good. For phi bar inverse and for phi bar transpose inverse. Maybe let's do this one only. This one you can also do it in terms of the matrices phi bar and n. Okay, let me remind you of the previous. Yeah, this is meeting 24 here, the same slide, and if you just go up, you see this is my annotation after class. Right? I basically explained to you that to find the initial model, the model initial condition, in terms of the initial condition, you can invert the matrix phi bar, or you can use orthogonality to obtain this expression. So then the question would be, well, first, why? Can someone remind the class why? Why you want to avoid this, but use this? Can someone, let me bring someone new, let's say KZ.
It's very expensive. Very expensive.
Very expensive to compute the inverse. Okay, keep in mind we are talking about not just 2 by 2, but 100 by 100, 1,000 by 1,000, 1 million by 1 million. Okay, the inverse is very, very expensive. But the transpose is free, and matrix multiplication is cheap. Okay. So if you look at these two expressions here, can someone express phi bar inverse in terms of phi bar and n? Should be obvious. Colton.
Phi bar inverse is equal to phi bar transpose times.
Yeah, phi bar inverse equal to phi bar transpose and m. But there is, this is like looking at the result, okay, and compare the results. So let me note down KZ and Colton. That's team 2. How about honestly derive that? Can you honestly derive that expression instead of, this is already in a derived form, meaning you are already at the bottom, at the result. But if you, so the question is, can you honestly derive this? Let me give you a hint. That should be in the previous handwritten notes. Let's see, maybe I can go to my maybe meeting 22. Yeah, it's right here. You see, it's in meeting 22. You see, this is how I derive this expression, right? Model initial condition in terms of initial condition, and using only phi bar and the mass matrix, no inverse. And how we derive that is by using the orthogonality condition, right, of the normalized eigenvectors. So can you get, so this is a hint here, can you get the expression for the inverse of phi bar using that one? Let me give you a hint. Okay, so the hint is as follows. And right here, let me go to the next page and bring up meeting 22, so I can copy the expression for right here, the inverse, the orthogonality, this one. To the new notes. Okay, and give you a hint, and this is the hint. Everyone knows that if you have a matrix A, and if you take A inverse times A itself, what do you get? Identity matrix, right? So clearly, if you take phi bar inverse times phi bar itself, what do you get? You get identity, right? Everyone knows this. So here's the hint. If you look at this expression and this expression, can you deduce the expression for phi bar inverse? Come on, active learning training.
Yes.
Just look at this expression in the orthogonality and the definition of the inverse of a matrix. Colton, you already, let's bring it higher.
For either value, either formula that you have is equal to the identity matrix on the left, you can divide either one of those by phi bar, and that will equal the phi bar inverse.
Maybe I should write like this, and you see maybe this is what I want to say. Okay, you can rewrite this expression, move this out a little, okay, and put, maybe use the blue color. If you put the parentheses around the product of the first two matrices, right? Multiply by phi bar equal to identity and compare to this, you know, obvious definition of an inverse that you can identify. That phi bar inverse must be phi bar transpose times n. Okay? That's the idea. So phi bar inverse is equal to phi bar transpose times n. And so once you know how to do this question, the next question will be also simple. That requires knowing a little matrix theory. Okay, so this is the inverse of a matrix, okay, of the transpose. And the inverse of a transpose is the same as the transpose of the inverse. So that's why you write like this. Okay, so, and once, so the next question is, what is the inverse of the transpose of phi bar? Okay, of phi bar. And IE. So the transpose of phi bar is this one, right? And the inverse is simply put -1. Okay, that's a superscript. So once you understand the reasoning up here, can someone find the expression of the inverse of phi bar transpose in terms of phi bar and n? The then
Is it just phi bar and m is equal to the inverse transpose?
okay. Maybe let me give additional hint. How about writing like this? What is this equal to? If you type phi bar transpose times the inverse of itself, what is this equal to? Identity, right? So the Van and Robert, the Van is team 6. And while I do this, why don't you think? This is a hint. The Van is Mtg.26, team 6, and Robert is team 5, right? 5. Any answer? More hints? Kevin, team 6. Right, let me give more hint for the class here. Kevin may already see. Okay, if I put these two together, maybe the class somebody would say, "Aha." Kevin.
Is it m phi bar?
M phi bar. Yeah, because you know, again, if you move this out and put the blue parentheses around, and then you can identify the inverse of phi transpose with m times phi bar. Okay. So let me do that. And therefore, from here, you deduce immediately that the inverse of phi, the inverse of phi bar transpose is equal to m times phi bar. Alright. That's it. So the idea is that you can replace the inverse by matrix multiplication, and that's cheaper, much cheaper. Alright. And the method is using orthogonality. Okay, so let's go back to the plan. And the plan is I'd like to coach you to do my own exam. Okay, any questions on, well, maybe I need to review a little, you know, problem 3. You know problem 3, I already wrote in detail. There are 2 methods, right? Yes, Mohammed?
Is that a general question?
Yeah.
So from exam 1.1,
Yes.
the second problem wasn't really covered. So will that problem potentially be covered on the exam on Friday, or is that just something we won't have to worry about?
Oh, so let me repeat your question just for everyone to be clear. Would the second problem in exam 1.1 part of exam 1.2?
Yeah, sure.
Yeah, so what do you want? Then you have 3 problems to choose and make it easier. So exam 1.2 would be either problem 3 or problem 4. Because you already studied problem 2 for exam 1.1 already. So, and like I said, you know, I mean, I prefer not to mention which problem because then students will not study the other problem. The idea is really to encourage learning. I know students sometimes is more motivated to learn because of the exam rather than the other way around. Okay, so let's you know, I have covered this very much in detail already. There's not much left. Now you know how to do normalization with respect to the mass matrix, and you know how to verify orthogonality. So probably I don't need to cover this. Is there anyone who needs me to explain? Feel free, okay? If you feel that you need me to explain, I'll be happy to do so. I know your name. Just Team 7, I know Team 7. And this should be Nicolas.
Yeah.
Okay.
Can you just say which lectures that you went over the whole problem 3?
Oh, you know, it's. Let me show you the method of how to do that, okay? Instead of saying which lecture, because it's not easy to really remember which lecture number, but here is how you would do. So let me bring up the daily lecture summary. You know, like I said, this is a very important document that I advise students to look at this document every day, so that you get used to it. If you wait for 2 weeks, just before the report is due and go to this document, you could be overwhelmed because of the amount of information. Okay? And it would be worse just to wait before the exam. So don't do that. Now, method. The method that you know, Nicolas asked. You know, how do I find, or how do you find the sections that are related to certain topics on the exam? Okay, again, this is motivated by exam, but okay, that's how students learn. You know, whenever there's that I coach students to do my own exam, I have the word practice, so you can search. So Control F. So this is search. You see on the top right corner, there's a search box there. you type practice. Okay, then you see that you would get immediately to the meeting where I explain the practice problems for the exam. And if you see the green background, that means that I talk about this in this meeting, right? I explain this in this meeting, then you can look at my handwritten notes. You bring up my handwritten notes and you see essentially I explain how to do, you know, this is an example, right? This is problem 1 in exam 1.1. Okay, so that's how you search for the meeting numbers where I train students or coach students to solve my exam problems, and then look around for the section numbers. And another method, can someone remember another method to find this? Given a topic, say generalized eigenvalue problem, how do you find a section of my lecture notes that talks about the generalized eigenvalue problem? There's many methods. You can search for generalized eigenvalue problem in this document, right? Is that the obvious way? So Control S, let's say generalize. Yeah, let me see section 53D. Okay, or you can go to the list of topics and do the search. That's how you find my lecture notes. Okay, but you know, time is precious, so you probably want to hear me talk more about how to solve these problems. So is it a good assumption to assume that everyone knows how to do question 1D and 1E, and also DEF here? Yes.
How would you verify the orthogonality?
Caleb did. Yes.
How would you verify the orthogonality?
Okay, so the question that Caleb asked, Caleb is team 2, team 3, team 5. Okay. So while I do this, why don't you think? Caleb asked, how do you verify orthogonality of the eigenvectors, right? After you have solved for the eigenvalues and found the eigenvectors and normalized the eigenvectors, how do you verify? Oh, sorry, this is verify the orthogonality of the normalized eigenvectors. Kevin already contributed, and Frank?
You use the relation we just used with phi transpose times mass.
That's right. Use the relation that we just used, because in this question D, you already found the normalized eigenvectors, right? Phi1 bar and Phi2 bar. And now you want to verify orthogonality of the normalized eigenvectors Phi1 bar and Phi2 bar. You use the expression that I just wrote down here, like Frank said. You know this one? This is a very important expression, right? Phi bar transpose M phi bar equals identity. So if you take phi bar transpose times M times phi bar, if you get the identity matrix, that's it. That's the verification. But there's a shorter way. Can someone think of a shorter way? You know, multiplying these 3 matrices is a little long. I want to show you an even shorter way. What is the shorter way? If Kevin raised his hand, and Kevin, if no one else, then Kevin would take over. 1, 2, 3. Kevin.
Next, just take the dot product
Take the dot product of what and what?
of the eigenvector and the.
Take the dot product of the eigenvectors Phi1 bar and Phi2 bar, right? Okay, very good idea. So let's try that. Okay, so because you know the question is ask you to verify whether Phi1 bar is orthogonal to Phi2 bar. And this is a question. So Kevin said, well, take the dot product. So, okay. So you replace this inverted T here with a dot product. And you check whether it's 0 or not. Right? Is it the right method? Anyone? I note it down, Caleb already. Anyone in the class? Come on, come on. Yes. Press 2, excellent.
Yes.
Yes? Okay. Okay. Anyone else? Press 2. No, it's very important to participate because that way you remember better. Okay, so I don't care whether the answer was right or wrong. You know, you heard that this is orthogonality with respect to the mass matrix. So what you want here is the generalized dot product. And the generalized dot product is when you stick the mass matrix in between. Okay. You can write like this. That's one way. Or you can write like that. You know, if you want to see the dot product, you simply just replace the superscript T for transpose by a dot and put the parentheses around that. Okay, so that's the same thing. Let me write down here. And so what I'm saying is that these two expressions are the same. Okay? So you can think of this as the generalized dot product, but I suggest use this form. Okay? And so if the result is 0, then phi1 bar is orthogonal to phi2 bar. Okay? So maybe let me write like this. Phi1 bar is orthogonal to phi2 bar. Implies that this generalized dot product equal to 0, or vice versa, meaning that if you can verify that phi1 bar times m times phi2 bar equal to 0, then you can deduce that phi1 bar is orthogonal to phi2 bar with respect to the mass matrix. Okay, that's very important. Okay, so next. So all of the issue for problem 3, I hope is clear to everyone. If you have questions, feel free to ask, but I'd like to move forward here. You know, problem 4, actually I can make both problem 3 and problem 4 together, but I split into 2 because if you make a mistake upstream, then it will propagate throughout. Okay? So that's why in problem 4, what I did is I give you the eigenvalues. Let me zoom in. So in problem 4, uncoupled from problem 3 in the sense that I give you the eigenvalues, I give you the modal damping coefficients A1 and A2. So these are the eigenvalues here. These are the modal damping coefficient. Why do you know? Well, you need to look at this expression here, right? That's yi double prime plus ai yi prime plus beta I yi equal to ri. So these are the two modal equations, right? Because I equal to 1 or 2. These are two modal equations. So ai is the damping coefficient, and beta I is the eigenvalues. Okay. So the eigenvalues are given. Hey guys, could you please quiet down? Yeah, so these are all given. I give the eigenvectors, not normalized here. And there's a misprint here that when I worked with Jackie, we found there should not be a bar here. That just this is just phi no bar, okay? No bar on top, because it's just the matrix of the unnormalized eigenvectors. Okay, and the mass matrix is given here. These are the model initial conditions given also. So the first question is write the linear second order ODE for mode 1 and solve for the model displacement y1. That's very simple, right? Because you have already the equation here. All you need is just to replace the numerical values, right? You have, let's say, for I equal to 1, model equation for mode 1, right? So that would be y1 double prime plus a1, which is 2/3, times y1 prime plus beta 1, that is 9, times y1 equal to r1, and r1 is equal to 3. So then you would solve for y1. It's just a simple linear second order ODE with constant coefficients, and the excitation is a constant function. R1 equal to 3. Okay, so no one should have problem with that. You need to review how to solve linear second order ODE. We have done that several times in class. I have the extra lectures. You need to use those resources. There's videos and lecture notes. And then you do the same for mode 2, right? So mode 2 would be y2 double prime plus a2 y2 prime and y2, sorry, a2 y2 prime and a2 is equal to 10 plus beta 2 y2, and beta 2 is, I wrote on top of this, and the number should be 16 or something. I think that you can move a little. Yeah, 16. Okay. And the excitation R2 is equal to 0. Okay, so that's a homogeneous equation. So this, the second model equation is a homogeneous equation, simpler than the first model equation. So question 2 should be no problem. Question? You know, if you have any questions, please feel free to raise. I'll be happy to answer. Otherwise, I assume that this is easy. Question 3. Verify orthogonality of the eigenvectors with respect to the mass matrix. You know, the eigenvectors are given. Because you see, I decoupled the two problems. So essentially, I solved the eigenvalue problem for you, the generalized eigenvalue problem for you, and it gives you the eigenvalues and the eigenvectors. So all you need to do is complete the second part. You know. And so this question 3 here is what we just did. You know, with the exception. Sorry. With the exception. With the exception that this is not normalized yet, okay? So you need to verify with respect to the mass, and then after that you normalize. Anyone has problem with this? How to do this question? Otherwise we go to the next one. Find the displacement matrix D of these two degree of freedom systems. How do you do that? Right, so assume that you have solved for y1, you have solved for y2, you know, meaning you solve for y1, and y1 is in question 1, y2 is in question 2. Question 3 is just verifying the orthogonality of the eigenvectors, Nicholas.
I was going to say you find displacement by plugging in the initial conditions into the solved differential equation.
Yeah, so you know, when you solve for y1 and you solve for y2, you should have satisfied the model initial condition. Okay, Casey?
So for E, you time your modal displacement by V bar.
Excellent. That's it. Okay, so what Casey said is the following, and this is, we have done this many times. And if I write down the expression, you say, aha, you know, you have seen this many times before. The matrix D, the displacement matrix, is the matrix of the normalized eigenvectors times the matrix of the modal coordinates. Okay? Right? Everyone remember this? What is the pedestrian way to do this? You know, remember, phi bar is a 2x2 matrix. And Y is a 2x1, right? And D is a 2x1. If you use a pedestrian method, thank you, Casey, you would avoid doing matrix multiplication. So what is the pedestrian method? Can someone remind the class? Okay, remember this can be written like this. You know, the matrix phi bar is the matrix with the normalized eigenvectors in the columns. So you have column 1 is phi 1 bar and column 2 is phi 2 bar, and the matrix Y is Y1, Y2 as a function of time t. So if you multiply out, the pedestrian method is simply that. Right? You just put the eigenvector here, that's a 2x1, times the expression of the modal displacement y1 plus 2x1 second eigenvector times the modal displacement y2. You found, so y2 is found in question 2, y1 is found in question 1. The unnormalized eigenvector was given. All you need is just to normalize it. Okay, that's it. And then you combine, get the displacement. Okay. So these are lecture summary. Just one last remark, okay, regarding the damping matrix. I give it here. So just last remark. You know, you have this relation, right? Phi bar transpose C, phi bar is a diagonal matrix.